Hello class, welcome back to Introduction to Materials Science and Engineering. This lecture will cover deformation and strengthening mechanisms. We will concentrate mainly on metals, but we'll also pick up some of the unique ways in which polymers, especially thermoplastics, can deform without fracturing. This is following on from our Chapter 7 lectures and discussion. That's Chapter 7 in the 4th and 5th edition of the Callister text on mechanical properties. And just to review our coverage in the course to date, our first portion of the course we focused on atomic bonding, microstructure, mechanisms of deformation, properties of materials, very much at the bonding and microstructure level. We looked at why things happen at that very small scale level. Then in the case of Chapter 7, or mechanical properties of materials, regardless of which textbook you're using or which chapter you picked up there, we panned out from that and we lumped all of those mechanistic effects into constants like Hooke's law, constants of elasticity, your Poisson's ratio, and your Young's modulus. We lumped all of the effects of dislocation movement into a yield stress. We lumped all of the effects of dislocation, entanglement, and interaction into the difference between yield stress and ultimate tensile stress. And likewise properties about creating surfaces in a material when they fail into fracture onset, strain at failure, as well as fracture strength. Now we're going to do a hybrid between. We're going to keep one eye on our macroscopic or continuum properties, as we did for the mechanical properties discussion that we just finished, but we're also going to put an eye back to our defects discussion, where we discussed what are dislocations, how they move, and how do they relate to stress to deform a material. So we'll jump right into it. Deformation and strengthening mechanisms. We're going to look at the role of dislocations in deformation, which if you are a crystalline system is pretty much everything. We're going to look at slip systems and critical resolve shear stress. So for that we will be doing a quick force balance, but also looking back a little bit to our crystallographic orientations and slip planes. Microstructure for preventing dislocation. That is truly the heart of this discussion. What do we need to do microstructurally, mechanistically in a material to keep dislocations from moving if we don't want them to move? And then processing. We're going to pick up on some of that for the first time. Thermomechanical treatments to achieve deformation-resistant microstructures. So basically, what kind of microstructure do we need to keep dislocations from moving, and then how do we actually make that in a material? So how do materials deform? So if you remember anything from our defects section, you should be raising your hand and saying, well, if you're a metal, it's by dislocation movement, which is absolutely right. And the lower the stress needed to move a dislocation, the lower the stress needed to yield and plastically deform. So if dislocations move easily in your material and you have a crystalline material, your yield stress will be lower. So that 2% offset yield will come at a much, much lower stress than in something where a dislocation requires more stress to move. They're totally analogous. We did discuss that dislocations move easier on certain crystallographic planes than others, namely close-packed planes are ones upon which dislocations like to move, and close-packed directions are the directions in which dislocations like to move. So if you have your applied stress on your crystal or your grain, if you have a polycrystalline material, aligned to push the dislocations on those close-packed planes, it won't take as much force to move them, or as much stress, force per unit area on the grain. Stepping back from that, materials that don't have as many of those close-packed directions and close-packed planes are going to have a much more limited ability to deform. And the most glaring example of that is the hexagonal close-packed system, which encompasses quite a few engineered metals, zinc mainly, and so these materials might deform easier by twinning than by dislocation movement, because although in the case of hexagonal close-packed or HCP, there is one close-packed set of planes, but only one. So those dislocations will initially move easily on that and then quickly max out the capabilities to sustain more deformation. dislocations pile up and interact and don't want to use that slip system anymore, and then there isn't anything else to go to for that crystal system. So you will see twinning in systems with limited capability to support dislocation movement. If we look at ceramics, those, although they are crystalline materials and they do indeed have dislocations, it is very, very difficult to move them because the covalent bonding angles don't want to accommodate dislocation movement in the case of covalent crystals like metal oxides. In ionic ceramics, moving a dislocation involves bringing like charged species, the anions and cations, into very, very close proximity. And so you can imagine that your Coulombic repulsion in that case is going to be pretty strong. And so generally, regardless of whether you have an ionic or covalent ceramic, and despite the fact that they do come preloaded with dislocations, the stress required to move those dislocations quite often is less than the stress to fracture. And so we really don't have the capability of moving our dislocations in ceramics, and so they basically have very low ductility and fracture toughness. Polymers can move by dislocation movement if they're highly crystalline, but they don't need to. They have another way of moving, and that's by extending the chains in those amorphous areas that surround all the crystalline areas. So they've got multiple ways they can move, as opposed to metals and basically, and we'll compare those two. Metals can really only move at least at room temperature by dislocation movement. Polymers can move by chain extension in the amorphous areas and by rotation of the crystalline areas in the direction of stress, and also by dislocation movement within their crystalline areas. So they have a lot more options. Okay, so just going through this graphically, kind of what we just said. Metals, dislocation movement is easy. Remember, we have that electron sea of bonding, so there is no particular angle or position that metals atoms need to favor one relative to the other than simply wanting to be at that equilibrium interatomic spacing. Beyond that, every electron is the same to every ion core, and so a dislocation can move through the material fairly easily and in general in multiple directions. Covalent ceramics, again, dislocation motion is difficult because either you have very set angles in your bonds set by your covalent bonds, your hybridized orbitals. Your sp3d wants to be at a certain angle, and so a dislocation moving through that is going to have a hard time disrupting that and need a lot of stress to move. Again, probably more than stress to create a surface. And you can see here in an ionic crystal, for that dislocation to move through that crystal of alternating positive and negative charges, at some point those two positive charges will be in close proximity to one another. They'll have to move over and be pretty much lined up with one another, and likewise with the negative. So as the dislocation goes through its point of maximum energy, not only are we moving atoms out of their equilibrium position according to our potential energy well, and increasing the strain energy between them, we're also encountering a tremendous amount of Coulombic repulsion, so it's kind of a double hit. And again, just as was the case of the covalent ceramics, this is going to lead to a situation where it's easier to create a new surface in the material than to move a dislocation, and so that means it's easier to fracture than to yield. So hence the brittle nature of most ceramic materials. Okay. Looking back at our friend the edge dislocation. So we're back to looking end-on at a metal crystal lattice here, and you can see that over on our left-hand diagram we have an edge dislocation, and that's the plane of atoms labeled A, second from the left within our crystal, and it ends 3 atomic rows down from the top of that schematic. So the next layer of atoms down below the end point of the dislocation, that's colored in slightly darker colored blue, that is the slip plane. And the higher the atomic packing fraction of that plane, the planar packing that we learned in chapter 3, or we learned in our crystallography section, irrespective of the chapter number, the easier that edge dislocation will move on it. There is an analogous situation to screw dislocations, which I'm not going to try to describe and envision, but it works exactly the same way. So the dislocation will move along that plane with much less applied shear stress if that plane is close packed. Likewise, if the direction of movement of that dislocation is in a close packed direction, less stress will be required to move it. So, and again, if that dislocation can't move, plastic deformation can't occur. Oh, just to revisit there, looking at the rightmost diagram, now that we've discussed stress and strain in the context of a uniaxial tensile test, we can see that our unit step of slip that's labeled on the rightmost side of the rightmost schematic, that is a small contribution to the overall strain of the material that we measure in our uniaxial tensile test. So that unit step of slip is literally a unit step of plastic deformation or plastic strain that we would measure in our test. Okay, dislocation motion. So we can start adding up this motion for small crystals, which will be grains in a polycrystalline material, and start relating this to ultimately the stress that we have to apply to a whole sample or to a whole part in service. So thinking back to the previous slide, the dislocation moves along a slip plane, and that slip plane is shown as the plane marked on the left-hand most schematic, where the upper and lower portion of the blocks are displacing relative to one another. That's the shearing plane, shown kind of by dotted lines. We have an edge dislocation moving from left to right in the direction of the fuchsia arrow, and the applied shear stress with the teal arrows on the top and bottom with the shear symbol tau is providing the stress to move that edge dislocation. So it's moving along the slip plane and in the direction of applied shear stress to result in that step of deformation. So stress is leading to strain via the movement of that edge dislocation. Okay, slip systems and crystalline materials. A slip plane is the plane on which easiest slippage occurs, and these are crystallographic planes in the case of our metals, which are deforming. The highest planar densities have the largest interplanar spacings, and that is indeed why those high densities, those closer packed planes, are easiest to slip. It's easiest for the atoms to basically move from the compressive to the tensile position and allow the dislocation to index across, and the same with the highest linear densities in the direction of dislocation movement. So for the purpose of this class, the two that we really need to remember, and it's obviously more complicated when we get into polycrystalline materials, but we do need to remember for our two most common crystallographic systems for structural metals that our 111 crystallographic plane in the face-centered cubic system, the FCC system, is our close packed plane, and that is going to be the plane upon which dislocations will move easiest and move first. And on those planes, the dislocations will move first in the close packed direction, which is your face diagonal, where all the atoms are touching. So that is the 111 family of directions. So to repeat, even a face-centered cubic system, which is things like, I believe, aluminum, I believe silver is face-centered cubic. Feel free to go ahead and check. All of those first row transitional metals that end up in so many structural applications, many of them are face-centered cubic. If you have the dislocations that are already in the material will move easiest and first in the 110 direction and on the 111 planes because they are close packed. So as you start to apply shear stress to any given grain within the material, and there's probably a lot of grains, those are the planes and directions on which dislocations will move first, and will therefore, those grains will deform first plastically. A body-centered cubic, by contrast, does not have a close packed plane, but it does have lots of close packed directions. We discussed redundancy of slip systems possibly when we discussed defects, but we'll do it again here. If we didn't, we'll catch it. If you remember your body-centered cubic unit cell, the close packed directions are any direction that goes through a body diagonal. And there's a lot of equivalent body diagonals. So although they don't represent close packed planes, and therefore compared to an FCC crystal, they're going to require a little bit more stress to get those dislocations moving, there are a lot of different directions that dislocations can move that are still close packed directions. So if you want to compare FCC and BCC, because FCC is a close packed, a true close packed crystal structure, it will be easier to get dislocations started moving in an FCC system, all other things being equal, because it has those close packed planes and directions to move. But it doesn't have all that many of them, and so when you start to exceed the capacity of those particular close packed directions and planes to move, the stress required to activate the next easiest system is pretty high. So you'll have a fairly low yield stress for any given crystal, but you might start increasing the stress after yield fairly quickly. So you would expect maybe a fairly big gap between your ultimate tensile strength and your yield strength in that case. Body-centered, on the other hand, requires a bit more stress to get dislocations started moving because there is no close packed plane. But once they're started moving on those 1-1-1 directions, those close packed directions, there are quite a few of them available, and it will take quite a while for them to effectively max out their capability for dislocation motion, and so you'll get quite a bit more ductility from those materials. They'll have a higher yield, but the difference between ultimate tensile strength and yield will tend to be lower. And that's very good for us because BCC includes iron, which requires a lot of deformation, and quite often we would like a high yield stress. Okay. Now, so far we've been talking about shear stress for a single crystal or even a single dislocation moving on a single set of planes within a single crystal. Well, that's great if we're working with single crystals, but if we want to build something out of a material, we probably need quite a few of them, since at least in metals, single crystals are in the form of grains, which are on the size of microns, and we probably want to build something on the size of at least centimeters, if not meters, or even kilometers. So we need a way to relate the applied loads and stresses to the shear stress at any point in the material that we could then start applying to those crystallographic systems. And lucky for us, all we need to do is a little bit of vector algebra. So this is an example of the relationship between an applied uniaxial tensile load, which we see in most of our material testing. So it's a very convenient system to look at because this will give us a relationship to our test data, and the resolved shear stress at any plane in the material at any orientation with respect to the applied stress. So we call that resolved shear stress because what we've done is we've resolved the vector loads or the vector stresses that we applied to the material. Remember, we control what we apply, but the geometry of the material determines what is actually seen at any point in the material. So that's applied loads versus resolved loads, or loads in a given direction in the material stress state is an important distinction to keep in mind when you're looking at an actual service application or analyzing your test data. So if we take a look at our loaded material over in the left-hand diagram, we have a force that we're applying to our sample, and say we have a little, say this is a uniaxial tensile sample, which pretty well oriented to be cylindrical. We can yank on the ends of it. So our applied stress is simply going to be F over our red A. Now the stress that we need to move a dislocation, though, is going to be a shear stress, and it'll probably be a maximum at some angle with respect to our tensile stress, because a tensile, in our tensile axis we have, in that direction we have no shear stress actually. So if we look at a green plane somewhere in the material at some angular orientation to our applied stress, you can see that we would have an F sub s, meaning a shear force, parallel to that green plane, and that green plane has an area A sub s. The stress that's going to move our dislocations is the green F sub s over the green A sub s. So that's our actual shear stress on a given plane within the material. So if we want to calculate that shear stress, which we're showing as tau sub r in the middle of the diagram, as a function of our applied normal stress, sigma, and remembering sigma is the typical symbol that we use for normal loads, tension or compression. In this case, it's our applied normal. All we have to do is multiply by the cosine of two angles. One is the angle between the applied load and the slip direction, and the other is the angle between the applied load and the normal to that slip plane. I'm not going to go through the derivation of that in lecture, but we could do that if you have a live class session with this course, or you can just do that on your own with vector algebra. This is basically just a statics problem. So what you're looking to do is find the force per unit area in a given direction where that force is parallel to a plane. So you're going to be looking at that green area. Actually, it is larger than the red area, and so you're looking at force per unit area parallel to any plane at any angle within the material. So it's just a geometric relationship there. So the important thing from our standpoint when we're looking at analyzing uniaxial tensile stress data and relating the applied stress to our sample with that shear stress that might be moving a dislocation in a grain somewhere within our sample, is that for a uniaxial normal stress, sigma, or normal stress, our resolved shear stress is maximized at 45 degrees from that applied, the direction of applied normal stress. So shear, this is only for uniaxial tension, not biaxial and triaxial applied loads. So if we're applying loads only in one direction, a tensile or compressive load will have an associated maximum shear load at 45 degrees. So any favorable slip plane or microstructure upon which a dislocation might want to move will also move first if it happens to be oriented at 45 degrees. So that just based on the geometry of force resolution. So now we have a double dependence. The material is preloaded with dislocations, and if it's polycrystalline, you have those crystallographic systems also oriented randomly all over the material in every direction. The dislocations that will move first are the ones that are simultaneously oriented such that their slip planes are at 45 degrees to the applied uniaxial tensile stress and are also close packed planes and directions. So there is a bit of a hierarchy of which systems will activate first and allow dislocation movement first. And of course, beware that angle with respect to applied stress for your for your maximum resolved shear stress will change depending on how many axes you've loaded. The 45 degree maximum will not count if you have biaxial or triaxial loading. This is only uniaxial tension compression relationship. Okay, so we talked about how most samples are polycrystalline and most materials, metals especially, that we use in practice are polycrystalline. Single crystals are pretty much the province of optics and electronic materials, or in a very few cases metals are used in the single crystal form for high temperature applications, but that's very much the minority. So to review, if we're gonna move dislocations and achieve yield and plastic deformation in a polycrystalline material, we have to move those dislocations only within a single grain. Now we have another effect coming into play. We can get those dislocations within each grain moving, and they will move first depending on grain orientation of our slip systems relative to our applied stress. But they can't move forever because dislocations encounter quite a barrier to movement when they hit a grain boundary, something we discussed in our defects discussion. So each one of those grain boundaries is going to be an inhibitor to dislocation movement. The dislocation can move all the way across a grain, it'll hit the grain boundary and pretty much stop in most cases, or require quite a bit more stress to continue its motion on the other side of the grain boundary. Your slip planes and directions are going to change from one grain to another simply because they're oriented in different directions. Likewise, the resolved shear stress will vary from one grain to another depending on how it's oriented relative to your applied loads. So in general, the grains with the largest resolved shear stress, like we just said, will yield first, and with another weighting factor for those for which you have easy to move systems also being lined up with your resolved shear stress. And so again, this is kind of reiterating that favorable grain orientations move first until all of their dislocations basically pile up at the grain boundary, then the others move. So what this does is it creates what we call cold work induced anisotropy, or texturing. So if we start with a material, this is just an optical photomicrograph, so this is a cross-section of a polycrystalline material, probably as cast or as recrystallized. So over on the left, we call this an isotropic microstructure, so the properties are the same in every direction. That's because the grains are equiaxed and randomly oriented. So if we apply shear stress left to right, the dislocations in each of those grains that are on slip systems that are oriented to take advantage of that are going to move first. If we were pulling it in uniaxial tension, we would have obviously our highest shear stress in a diagonal across the material. But regardless, whichever grains are lined up to take advantage of the maximum resolved shear stress based on the applied loading and are crystallographically oriented such that their closest packed planes and directions are also lined up with that resolved shear stress, they're going to move first, and as a result of their dislocation movement, they're going to deform and elongate. And we're going to see a selective elongation of the favorably oriented grains with each increment of deformation or increment of shear stress. And so you can see on the right-hand side, several of those grains are not equiaxed. They're now elongated, mostly left to right. But there's a few in there that are still more or less equiaxed. And those are the ones that were not originally oriented to take advantage, as good advantage of the directions of applied shear stress. Eventually, with additional applied stress or additional required strain, those will deform as well, but they will require more and more stress to do so. So the less favorably oriented your grain is, the more stress it's going to require to activate and move those dislocations. So what we end up doing is inducing a state of anisotropy in our material so that we eventually get something that's going to act mechanically more like a fiber composite. The structure on the right has much stronger properties in the left to right direction than it does in the up to down vertical direction. This is otherwise known as axial versus transverse with respect to the forming direction. So we effectively induce anisotropy or composite-like properties in materials, in crystalline materials, simply by deforming them. So that's something that we will take advantage of, but also have to be cautious of when we look at the effect on fracture. Okay, so by now we've covered how dislocations move, what direction they want to move in first. Hopefully we've emphasized the fact that if we want to deform a crystalline material, the only way to do so without fracturing it is to move dislocations. Hopefully it's obvious now that if we want a material to not yield at a given stress, or we want to increase the stress before it yields, all we have to do is stop the dislocations from moving. So how do we do that? Mainly we put things in their way, or we make sure that those strain fields that they have above and below themselves have to interact and repel one another. And we do this by refining the microstructure, usually by thermomechanical treatment. So our strengthening strategy number one, and there's several of them we'll go over, is to put more grain boundaries in the material. We picked this up in our discussion of defects that the dislocations move the easiest in given crystallographic directions. They like a regular order in which to move with the lowest applied stress. When a dislocation that's moving in a given direction encounters a grain boundary, it requires a lot more stress to continue its movement in the next grain. So you can think of grain boundaries as being dislocation barriers. And the higher the angle of mismatch between grains, the higher the barrier. This has been very thoroughly studied over decades, and has actually resulted of the accumulation of all of these studies has resulted in a relationship between yield stress and average grain diameter, and it's called the Hall-Petch relationship, and it's shown in the equation at the bottom of your slide here. And so as you refine grains and therefore introduce an increasing amount of grain boundary surface and decrease the distance a dislocation can move before it hits a grain boundary, you're going to increase yield stress. And it's a negative 1/2 relationship. So your yield stress is going to be related to a constant stress times another constant times your average grain diameter to the negative 1/2. So again, that's important to remember that the smaller the grain, the higher the yield stress. And this just means no grain within the material can deform as much until the dislocations hit a grain boundary, and that literally limits the amount of slip that each grain can undergo before the dislocations say, hey, give me more stress if you want me to move to the next grain. Okay, second strengthening strategy. Now we have to go back to our concept of elastic strain energy. Remembering in our discussion of defects, when we start putting point defects on a crystal lattice, we induce a state of either compressive or tensile strain as we ask atoms to move off of their equilibrium strain-free positions, thinking of our atoms in a crystal lattice being kind of connected by a bunch of springs. When we discussed dislocations as line defects, we hit on the point that by jamming that extra plane of atoms in, we had created a state of compression above the end of the dislocation plane and a state of tension immediately below it. We can combine the induced stress states from solutes with the strain fields of dislocations and kind of get them to cancel out. So if you have a substitutional solute atom, like copper and nickel, or anything else that dissolves in solid solution, if you have a large solute, one that's larger than your solvent lattice, it's going to create a state of compression around it. That compressive state could interact with the tensile strain field underneath the dislocation, partially cancel out, and create a lower energy state. That lowered energy state means that the dislocation has less preloaded energy and is harder to move. You've made it happier where it is, so it's gonna require a lot more stress to get moving. It is less effective at allowing yield in a material. Likewise for an atom, a solute atom that's smaller than its solvent lattice atoms, it's going to put all of the surrounding atoms in a little bit of a state of tension. If you stuck that in the upper part of a dislocation in its compressive strain field, you'll cancel the compressive strain field out. And likewise, in the same way, make the dislocation less energetic, more stable, in place, less likely to move. So you're effectively canceling out elastic strain fields in a crystal lattice, lowering the energy state associated with the dislocation, and therefore increasing the amount of mechanical energy we would have to add to make it move. Now, it still requires way less energy to move even that partially stabilized dislocation than to move the whole crystal lattice by shearing every plane on the shear plane. We're still orders of magnitude below that, but we definitely will be maybe within a single order of magnitude changing the energy or the stress to move a given dislocation. So by using solute atoms on a crystal lattice to partially cancel the strain fields and dislocations and make them harder to move. This technique for strengthening is called solid solution strengthening. And all you have to do it is to dissolve a solute into a solvent. So basically make a solution alloy. That's it. You don't have to do any processing. You do this with composition. So here's some schematics that just give us a little bit more of an idea of how these strain fields interact. Say you have a solid solution alloy where you've got a smaller solvent atom on a lattice position, and that's shown over on the left-hand side. You've got that small solute atom, and all of the bigger solvent atoms are pulling in because they are not at the equilibrium spacing that they want to be, so you've got a state of tension. And a dislocation encounters this tensile strain field, and if those solvent atoms, or excuse me, small solute atoms are on that upper plane where the dislocation has a compressive strain field, they'll cancel and the dislocation will just sit there. Or it'll say, give me more stress to move. And the opposite for a larger solute. So you can see on the left-hand side you've got a large solute atom. It's putting its surrounding solvent atoms on the crystal lattice into compression. So it's going to want to migrate to that tensile strain field below the slip plane at the dislocation and cancel out part of that tensile field. So flipping back to the previous slide, small solutes, so our smaller sized alloying additions, which is another word for solute in a metal crystal lattice, they induce a state of tension. They're going to migrate to the compressive side of a dislocation. Big solutes, large alloying additions, meaning large sized alloying additions, they induce a state of compression themselves, so they're going to want to migrate to the tensile side of a dislocation, partially cancel the strain field, and increase the amount of stress needed to move that dislocation. Okay, completely different strengthening strategy, number 3, dispersions. So this is stepping away from the idea of the strain fields and more or less just looking at something that is like a super grain boundary. These are very effective for stopping dislocation movement at high temperature. This is called dispersion strengthening. So in this, you accept the fact your dislocation is going to move through the grain, but you give it something to get in the way that is going to stick around in much the same way as a grain boundary. You're going to give it a crystallographic mismatch to bump into. But if you want to do this at high temperature, grain boundaries may or may not be reliable because, as we'll discuss in a minute or two, they kind of tend to move and go away sometimes at high temperature. But if you put something that has refractory characteristics, that's a high temperature material in and of itself, as a dispersion, as a second phase within your microstructure, it's going to stick around. And so the boundary between it and the parent material, the parent crystal lattice, will always be there in your service environment at your chosen temperature, if you pick the right one, for a dislocation to bump into. So if you have a dislocation moving along through a microstructure, which you can see in our top schematic side view, it's being pushed in the direction of the green arrow on the left. So we have a left to right shear stress. It's going to propagate from left to right. It's going to hit this ceramic precipitate, this particle, a dispersion particle. It can shear through it, maybe, but it's going to require a tremendous amount of stress. If we look at how that edge dislocation, the end of that edge dislocation, is propagating through the material down from a top view, it's going to look like a line because it's a line defect. If you don't have enough stress to shear through your precipitate, which is probably good because it means you chose the right one, the dislocation can actually bow around it. That also takes more energy, and there are a limited number of dislocations that can now come through and continue to bow around. So this is called dislocation pinning. So there's 2 ways in which dispersion particles stop dislocation movement and therefore stop deformation. They can be weak enough that dislocations can shear through them, but require more stress to do so, or they can be strong enough that dislocations have to actually bend around them, and thereby they will pin the dislocations. And this works best, especially if you look at that pinning scenario. You can see there is a red letter S between any two adjacent dispersion particles. So there's your average interparticle spacing. The stress needed to yield the material is going to be proportional to the inverse of that interparticle spacing, because it takes a lot more stress to bow those dislocations around particles that are tightly spaced. Basically, you have a tighter radius of curvature on the path that you now make that linear dislocation assume. So if you want to strengthen a material with a hard particle dispersion, it needs to be very closely spaced, very fine dispersion. Just a few particles don't really do it. You have to have them small and really close together on the scale of the microstructure relative to the grains. And you can find quite often the actual interparticle spacing that's necessary for a given temperature and a given material and a given particle is something that you would have to work out empirically. There's a lot of literature data available on that, but I would be thinking in terms of micron scale at best, if not down into nanometer scale. Okay, strain hardening. So in addition to interacting with grain boundaries and interacting with solute atoms, dislocations can interact with one another. They have those tensile and compressive strain fields that are associated with themselves, and if they come adjacent to one another, those strain fields will themselves interact and repel, and therefore increase the amount of stress needed to keep moving them. So going back to our strain field and strain energy argument. This is true if we are deforming metals at less than about a third of their melting point. When we get more than that, we actually activate a whole different means of dislocation movement, which we're not going to look at now. But we'll at this point focus on dislocations interacting just with one another, independent of solute atoms, independent of dispersions, and independent of grain boundaries. And this is called strain hardening. So this is where we will alter a microstructure by deforming it, actually, in order to increase the number of dislocations in the microstructure and to increase their entanglement and interaction with one another, thereby getting those strain fields to interact and making it harder to move. So deformation itself, every time we move dislocations in a material and plastically deform it, again, apologies, this is again specific to metals or to polymers that are deforming by dislocation movement, which is more the exception, so think metals. Deformation increases the dislocation concentration and the extent of interaction. It's a double effect. You get more of them and they interact more. So obviously it's easy to think, well, hey, wait a minute, I needed dislocations to deform. If I have more of them, won't it be easier to deform? Yes, up to a point. Most materials, even without any kind of extensive deformation, have plenty of dislocations to allow all the deformation you want. So while a minimum concentration of dislocations is needed for plastic deformation, above that threshold, adding more dislocations per unit volume actually makes movement of any one dislocation more difficult. So in the context of cold work, increasing the volumetric concentration of dislocations means making it harder for them to move, increasing the yield, increasing the stress for dislocation movement. So deformation increases the extent to which the dislocations interact with each other and with the extent to which they'll interact with anything else. And the more they interact, the harder they are to move. So it's almost a triple effect. We deform a material, we increase the number of dislocations per unit volume that are present, we increase the extent to which they are interacting with one another, and we increase the extent to which they're interacting with anything else that was in the material, like grain boundaries or solutes or dispersion particles. And the more they interact, the harder it is to move, and the higher the yield and tensile strength of the material. And again, this tensile strength being our ductile tensile strength that we saw in mechanical properties, our ultimate tensile. Okay, so we'll take a quick look here at the strain fields, the elastic strain fields around dislocations, thinking about how they would interact, just two edge dislocations one to another. So this is looking at the effect of cold work on dislocations. We said they interact and it's harder for them to move. Why? Because we actually literally have like-to-like repulsion of the strain fields. There's, you can look at our schematic here on the bottom. We've got two edge dislocations. We're looking at them end on. And we have the compressive strain field above the slip plane and tensile on the bottom. As you get those two closer and closer, you've got compressive strain fields interacting with one another. That's very strongly increasing the strain energy of the material. They want to repel. They want to push each other literally apart to the other ends of the slide in the direction of the arrows shown. So if we were applying a stress to the material and one of those dislocations, say, piled up against a grain boundary or was pinned between dispersion particles, and we tried to push that second one up against it, it would require a lot more stress to come into close proximity to that first dislocation than it would to just move through a dislocation-free material. So this is sort of like strain field polarities repelling one another. So the closer dislocations are to one another, the more they interact. We call this dislocation entanglement. You can think of it possibly in the way a polymer chain would entangle, except it's a linear defect entangling, but it's a similar idea of repulsion by strain fields. So again, we increase the density of dislocations as we increase cold work, and dislocation density so it's called that in length of dislocations per unit volume of metal. Remembering that these are linear defects, so a carefully grown single crystal will have perhaps 10 to the third per square millimeter dislocation length per volume of material. So remember, dislocation length is meters length units and volume of material is meters cubed, so we end up with per length unit squared. Moderate cold working will increase that length per unit volume by 6 to 7 orders of magnitude. So 10 to the 9th to 10 to the 10th per square millimeter. So 6 orders of magnitude, we definitely have more likelihood of repulsive strain field interaction and hence higher yield and tensile strength. So that is the essence of strain hardening. So we can pan back and take a look at this kind of on continuum mechanics, macroscopic scale in the context of a stress strain test. So if we had low carbon steel and we made some tensile test bars and we took some material that was nice polycrystalline low carbon steel, and we had some that had no cold work, we just cast it, and this is, again, this is comparing something that has the same grain size. So we're not looking at grain refinement here. So everything else being the same, we have one that's as cast, 0% cold work in the teal curve, one with 4% cold work, so we've increased the dislocation density and we've moved a few, piled them up at those grain boundaries, made them interact with a second phase, whatever. And then we had another that we really deformed. We rolled it or we extruded it, probably rolled it or drew it as a wire to a 20% cold work. So that means 20%, or excuse me, 24 on this diagram. That's a percent reduction in area or a percent increase in length. You can see the difference, and then if we cut a tensile sample out of that, so we got 3 tensile samples, one with 0% cold work, one with 4%, and one with 24%. And we put in our Instron, we did a stress strain test, we pulled it to failure. The one with 0% cold work would have a yield stress down around 250 megapascals, and then it would work harden in the test up to a tensile, an ultimate tensile strength of about 450. and it would have a strain at failure of close to 25%. The one that already had 4% cold work wouldn't start yielding until 400 megapascals. So that 4% cold work, that dislocation pile up and the increased density of dislocations from the 4% cold work that we did before our test increased our yield strength by just shy of double. Changed the ultimate tensile strength some. Maybe you went up from 450 to 475, just eyeballing the diagram. If we put 24% cold work, cut a sample, pulled it to failure in the same tensile test, we wouldn't start yielding till around 500 megapascals. We wouldn't achieve ultimate tensile stress until almost 600 megapascals. But we'd have maybe only 12% strain at failure. So the dislocation movement that would have been manifest in ductility in the tensile test pretty much was already taken up in our cold work, in our 25% cold work. So as you increase the number of dislocations in a material and increase their extent of entanglement by cold working, by forcing deformation in your material as part of your processing, you'll increase yield and tensile strength, and you'll decrease ductility and toughness. So this is the most fundamental aspect of metals-based material processing. As we form a material to change its shape, to create a part, if we do it below 1/3 of its melting point, whether we wanted to or not, this is going to be the change that we have in the material properties, in addition to just the shape change of the material. Okay, so to reiterate, we've gone over 4 different strengthening mechanisms. One, the one we just looked at, was cold work. So we can just increase, we can just basically purposely deform the material and increase the density of dislocations and their extent of entanglement. We can increase the grain boundary surface, decreasing the size of the grains, grain refinement. We can dissolve things in our crystal lattice, solid solution strengthening, or we can put a very fine network of small, hard particles in it for dispersion strengthening. And they each have their own role. Which strengthening mechanism is best? Well, it depends. What do you need to do? Do you need to up the yield and the UTS? Do you need to make the material tougher? Do you need it to retain that strength at high temperature? A general rule of thumb is the strengthening mechanisms that are the most effective in service for a part you're really going to use are the ones that give you an increase in strength, in yield and tensile strength, with the least compromise in toughness. In general, all of these mechanisms will, in one way or another, increase strength at the expense of toughness and ductility. The strengthening mechanisms that extract the lowest toll in ductility and toughness are the ones that tend to be the most desirable and applicable, and not surprisingly, the most expensive. So there is no free breakfast in the metals or materials processing world, unfortunately. On the good side, you don't have to use just one. You can work harden an alloy as opposed to a pure material. You can use a combination of work hardening and alloying and grain refinement, and you can go in and put a dispersion of fine ceramic particles in almost any material and give it some strength at higher temperature. So quite often your cheapest and your most effective solution will be a combination of these strengthening materials, or excuse me, strengthening methods. And those, again, they may or may not be the cheapest. Maybe they will, but they will generally give you the best combination of properties. Okay. One more step in the processing sequence, talking about combinations. Strain hardening is rarely done in a single step. Quite often you will strain harden a material in combination with getting it into the shape you want. So if you think about metal wires, how did you get it into that small shape? Well, you probably started with a cast billet or a continuously cast rod, and then you drew it down in steps of cold work to make a finer and finer wire. Same thing with metal sheets or foils or any kind of shaped part. This is called forming or forging, cold forming. So this is where we're imparting cold work not just for the purpose of making a material stronger, but getting it into the shape we wanted. Well, we can do two things at once. We can change its shape and add just the right amount of cold work to get the strength we want. But materials are limited in the amount of ductility they have. And as you saw in a few slides before, at 24% cold work, you had a limited amount of strain at failure. If you need more strain to shape your material, to get it into the size and shape that you want, you can't just keep cold working or it'll break in process. And that's pretty expensive. That leads to what we call a high scrap rate, which is not so good if you're running a business and trying to make things. So what we'll do in that case is do our cold working in steps, and then we will alternately reset the microstructure by adding heat and using a mechanism called dislocation climb to eliminate some of those dislocations and reduce the dislocation density in the material. And take a look at this and go back and forth between slides here a little bit. If we have a lot of dislocations in a material, they can get all tangled up and their strain fields will oppose and make the dislocations harder to move. If you think about dislocations that are opposite, such that you have the jammed in planes coming in this case from the top and then from the bottom, and you get them closer together, they'll actually cancel out. The compressive strain field of one will attract the tensile strain field of another, and the two half planes will come together and actually form a perfect crystal. This is called dislocation annihilation, and you will actually completely release those strain fields and make the material easier to deform. You will lower the yield stress. In order for dislocations to be oriented kind of top to bottom to annihilate one another, they'll actually have to move vertically relative to one another. In order to get dislocated, they normally want to move side to side in response to shear stress. To get them to move up and down, we actually have to have diffusion, a thermally activated process. So we went over diffusion earlier as a mass transport process. If we want to get a dislocation to move vertically with respect to the shear stress plane, we have to basically diffuse it up or down. And for that, we typically need to add heat. So if we take a material that has that we've cold worked, we have a tremendous number of dislocations, lots of interaction of their strain fields, we've increased the yield, decreased the ductility, we want to recover some of that. We can't deform it anymore. We need to do a little bit more shaping. We got to get rid of some of those dislocations. The easiest way to get rid of them is to give them a little bit of heat, activate this dislocation climb mechanism, which is a little bit like diffusion, and allow them to annihilate. So when we do that, this is called recovery. It's actually a named thermomechanical process that just basically means giving a material some heat, letting those dislocations climb into a position where their strain fields are opposite, cancel out, and they actually annihilate one another. And so our dislocation density will drop. You don't need to add any more stress. This happens all by itself due to the strain energy that we've now preloaded into the material from our high dislocation density. Okay, so in addition to being able to do that with some heat, we can also do what I call the surface energy strain energy bank account transfer. And I'll refer to this little diagram because I think it's kind of the easiest way to look at it. We're going to go back to the idea of energy in a material. We've talked a lot about strain energy and strain in terms of our mechanical properties and being the area under the curve, the energy per unit volume in a material. And in terms of the concept of resilience, the volumetric elastic strain energy in a material. We have strain energy around the ends of dislocations and around solutes. So when we cold work a material, so if we start in the dotted green box, we've got a material and we cold work it. We add a lot of mechanical energy. We're going to increase the dislocation density, and in so doing we're going to increase the lattice strain. We have compressive and tensile strain fields at the end of all of those dislocations. Now we have a lot of them. There is a tremendous amount of strain energy in that material. We can add some thermal energy and activate some dislocation climb and decrease that strain energy a little bit. And in so doing, allow for a little bit more cold work. And you can see that where we followed the arrows down in a clockwise direction under the recovery section, we've activated dislocation climb. And we've got a little bit of decrease in dislocation density and a little bit of decrease in lattice strain. Enough that we've increased our fracture toughness a little bit, but probably not enough to continue massive amounts of deformation. Not enough to say do another 50% reduction if we needed it to form the material. So we've decreased the amount of strain energy in that material some, but not a lot. And that's indicated by those down arrows in dislocation density and lattice strain being a little bit small. If we follow our blue arrow around and add more thermal energy, usually by putting something back in a furnace, we can now start what I call the strain energy surface energy swap. The material still has a tremendous amount of energy in the form of elastic strain. You have a lot of atoms that are not in the position that they want to be relative to their equilibrium position, so we have that potential energy all locked into the material. One thing we can do with that is create more surface area within the material. Now, this isn't like a metal air surface like we would see in fracture. We can form more grain boundaries and swap some of that strain energy in the lattice from all those dislocations to more surface energy in the form of grain boundaries. And this happens spontaneously. This is a thermodynamically favorable spontaneous process. And what actually happens is the remaining dislocations that weren't annihilated in the recovery step move, rearrange, and form dislocation-free, strain-free little regions and actually line up and form grain boundaries. So you can think of this as forming new, small, completely strain-free grains in the microstructure at the expense of releasing a lot of that elastic strain energy that is resulting from all of those dislocations. And of course now we have a lot fewer dislocations. So strain energy is going down, dislocation density is going down, lattice strain is going down, grain size is going down, and surface area of grain boundaries in the material is going up. So it's strain energy to surface energy swap in the form of grain boundaries as surfaces. This is called recrystallization and grain refinement. So now we've swapped the strengthening mechanism of a high dislocation density from our cold work, our strain hardening, for another type of strengthening mechanism, which is grain refinement. This is how you grain refine a material. You strain it, add a bunch of energy to the lattice, and then start exchanging some of that strain energy for the surface energy of a smaller average grain size. Now, of course, if you leave in the furnace too long, we know surface energy is another high energy state, and the material will spontaneously attempt to reduce that, and that is by a process called grain growth or coarsening, where larger grains will grow at the expense of smaller grains. We will reduce the total surface energy of grains in the material, and you'll get a bunch of gigantic grains which are not strong, and we will kind of defeated the whole point of attempting to strengthen the material. So you want to stop the process either at the recovery stage or at the recrystallization stage, depending on what microstructure you wanted to achieve. So this is an example of one of those combination strengthening mechanisms where we can have any combination of strain hardening via cold work or grain refining via recrystallization that we used part of the strain energy from the cold work to set us up for. So you have to start with the cold work and preload the strain energy to get the recrystallization. But depending on how much you exchange, you can get a bit of both, or a lot of both. So this is again, an optical cross-section micrograph of a partially recrystallized material. So you can see there is a lower red arrow pointing to a big grain that is a large cold work grain, and you can see some vertical stripes on it, kind of like zebra stripes. Those stripes are actually the striations of slip from individual dislocations. So that's a large, very highly strained grain. It's got a tremendous amount of elastic strain energy locked into it. So we gave it some heat, and you can see the upper red arrow on the right-hand side pointing to a bunch of much, much smaller grains, probably 2 orders of magnitude scale smaller from the looks of it. Those have no striations. They have probably 6 orders of magnitude lower dislocation density. They are effectively strain-free, but they're very, very small, and these are the recrystallized grains. So those all emerged in this recrystallization step that you can see here on the right. So this material is partway through recrystallization. It's halfway through its strain energy to surface energy swap transaction. So the new strain-free grains nucleate, and they grow, and they will consume the highly strained grains eventually. So generally, in terms of mechanical properties, skip ahead here, depending on what we need for service, and or if we're going to continue processing and we need to do another forming step, we will want to stop our strain energy to surface energy swap somewhere in the recovery or recrystallization arena. We do not want to go into grain growth. So you can see this here. The blue line is the tensile strength of the material. The red is ductility. If we needed a very high strength application, we're going to put a material right into service. We would take the material out of the furnace. We would stop that. This is called an annealing process, where we add thermal energy to a material to start our strain energy to surface energy swap. It's a new term. That's what's actually going on. I will flip back. Apologies for missing that term. It's a new vocabulary. Every time we add thermal energy, these dotted add thermal energy circles, that is all encompassed in what's called the annealing process. And so that's basically just literally heating a material in order to drive a microstructural change. You can see that's in the red labeling. So we are annealing the material for the purpose, we're heating the material up for the purpose of letting the grain boundaries grow in density at the expense of our dislocations. So if I needed something that was less brittle, but still very strong, I might want to stop my annealing step somewhere towards the end of the recovery, where I may not have a lot of ductility, but I've still got a high strength. If I needed to go through another forming step with another heavy reduction in area, maybe to draw the wire finer or form an intricate part, I might go all the way towards the end of the recrystallization and stop just short of grain growth. And again, if I maybe had a high fracture requirement in service, I could stop halfway through where the lines cross. So at this point, your extent of annealing and the extent of recrystallization that you would want would be dependent on what you're going to do next. Grain growth is generally universally bad in terms of properties, with the exception of high temperature creep, where we do want large grains, especially those oriented in the direction of applied stress at temperature. For everything else, small grains are better. Grain refining is a great technique for increasing strength with a small hit on fracture toughness. So we never want to leave a material in the furnace long enough to get any kind of grain growth. And of course, if you're looking at the cost of your process and its energetic requirements and sustainability, there's never a reason to be consuming the energy that is required for these thermal processes for metals or ceramics any longer than they need to be. So do not leave your parts in the furnace too long. Polymers, okay? What happens if you don't have to move dislocations to move material? Polymers have those continuous, amorphous regions between crystals. In some cases, polymers are totally amorphous. So the whole concept of dislocation movement and strain field interaction and everything is now either out the window in the case of an amorphous polymer, or all of that is happening at the same time and in parallel with chain alignment and reorientation via these amorphous regions. So this diagram, a schematic looking at the progressive reorientation of a semicrystalline polymer, kind of gives you an idea of the difference between metals and polymer materials. This is a thermoplastic. It isn't, the chains are not cross-linked. They're not a big 3D network of covalent bonds, so they're being held together by chain entanglement. This is obviously a semicrystalline polymer with a little ordered lamellar areas being the crystallites. So if we apply a stress, like say uniaxial tensile stress in the vertical direction, the first thing we're going to do is pull those crystalline areas apart a little. We're going to allow the amorphous areas between them, which move much easier, to start aligning. The crystalline areas are going to rotate such that their own chains are in line with the stress. And then you're going to see a progressive increasing extent of alignment of the amorphous areas, and eventually the crystalline sections are going to pull out and stack on top effectively. And each one of these different steps is characterized by a different shape to the stress strain curve for a uniaxial tensile stress. And this is one of the reasons that we don't see the classic necking engineering stress strain response that we do in metals. If you want to think about it, polymers basically neck right from the get-go. I think we hopefully touched on that in our mechanical properties discussions. The biggest thing that you need to remember for polymer strengthening mechanisms and deformation is that their stress-strain relationships are really dominated by that spaghetti tangle of amorphous material that's between all of the crystals. That dislocation movement, while it's possible, and while it does play a role in polymer deformation, it's not the big mechanism. It's really movement of these amorphous areas that allows reorientation and reordering of the crystalline areas. And the name of the game is chain realignment in the direction of tensile stress. It's getting those covalent bonds that are along the backbones of the polymer molecules to orient in the direction of stress. And once they are, your yield and your tensile stress goes through the roof, and really there's very little ductility, there's very little reduction in area or elongation possible at that point, because now you have those strong bonds all lined up in the same direction. So it's more flow and movement of those amorphous regimes. And this is of course why polymers tend to deform viscoelastically. Those amorphous regimes, they literally do flow, especially if we give them a high enough temperature that they can move quickly. That is, unless we put a covalent bond across them. And that's what cross-linking does. So thinking about strengthening mechanisms for polymers and thinking about thermoplastics in terms of viscous flow and chains literally slipping past one another in those amorphous regions between crystallites. If we literally weld across the chains, they can slip a certain amount, but they're going to reach a point where they're going to yank up against those cross links, those cross welds. These are chemical bonds that not a literal weld like we would in a melted metal, but a chemical bond that effectively connects the chains. They're not going to be able to slip anymore, and that's what the bottom schematic on this slide shows. On the left-hand side, we have a random chain entanglement of a thermoplastic with the little blue connectors showing the chemical crosslinks. If we apply some tensile stress, the sigma, meaning a normal tensile stress, we're going to start unraveling. We're going to extend those chains out, but they're going to hit a point where they're going to engage those crosslinks and they cannot slip past one another anymore. So that is one of the most powerful strengthening mechanisms for polymers. It has the potential for changing modulus yield and strain at failure. It will have its greatest effect on strain at failure and on ultimate tensile. It may or may not change elongation depending on the crosslink density, but it will definitely change how well those chains can slip past one another completely, and that will have the effect on yield. Also have its greatest effect at high temperature. So it's going to stop that viscous flow in our viscoelastic materials. Okay, that is it. This was a very long lecture, and I appreciate your patience. Hopefully you've stopped it and paused as often as you needed. And we covered a lot of material here, but this is very important in understanding the differences, or excuse me, the similarities and the relationship. Let's get our words right. The relationship between our macroscopic properties, our yield, our tensile strength, our ductility, and all the microstructural mechanisms that we've been learning up to date. We've pulled in everything from Chapter 2, again, our potential energy wells and equilibrium interatomic spacing, the genesis of those elastic strain fields. We had some crystallography. We pulled in the role of polymer structures. Our crystalline defects were front and center as our actual yielding mechanisms in the case of dislocation movement. And then we looked at different ways that we can put those all together and have them interact to stop dislocation movement in various different ways that will not compromise the material toughness. So the next big topic we'll jump into, we'll kind of reverse direction and look at the consequences of strengthening and the maybe more negative effects of not letting dislocations move, and that is fracture and a lot of our different material failure mechanisms. So again, strengthening is a double-edged sword, and we will discuss that in great detail in the next sections. See you then.